Okay, so as I mentioned in previous class, I will talk about affinity chromatography in more detail. So let's begin with focusing on the protein basically. So the previous one is focusing on the resin side, so resin and NTA structure, which is N and acetate, and then there's a nickel coordination, and then the two imidazole from the histidine comes and they make a whole the coordination system. So this is a resin focus. So now a little different aspect from the protein focus. So now the proteins with the sequences methionine, alanine, glycine here. And then as I mentioned that we need some the series of histidine residue, for example. So histidine, so the 6 histidine. So the first question is, so question number 1 is the protein with a histidine tag, right? This is a histidine tag. Requires removal. So that means is it has to be removed at a certain point because it is not a native structure. It's not a native sequence of amino acid. So anyway, at some point you have to remove. So the first question is not finished yet. So then the question is on which side the histidine tag attach it. The question is histidine tag, which side attach it. So the question is either N-terminus or C-terminus. So N-term versus C-term. N-term means you have an N-terminus. When you think about when you read the protein sequence, then you have NH2, and then you goes to all the amino acid, and then you have a COOH. Right? So in fact, there's an NH3 plus. This is COO minus in a solution, right? N-terminus sequence, C-terminus, right? This is a protein that we want to purify. Then where you attach this histidine tag? On here, or here, for the engineering aspect. So right now, the information I give you is not enough actually for you to actually answer this question. So that's why I'm using the second topic to explain this. Then there is an enzyme. To answer this, there is an enzyme. There is an enzyme that cleaves, right? Cleaves such a sequence, right? Cleaves the histidine tag. So require an enzyme. So that means you have, imagine a solutions with a histidine tag, nickel NTA region. You pour the solutions, all the proteins without histidine tag flows through it. You throw this away, and then you got an attachment of the histidine tag containing protein on resin, and then you put the imidazole or acid solution, so that histidine tag protein goes in. So you got some successful purification of protein. But now the next question is how to remove this one. So you need an enzyme to actually cleave out to remove this. So that's the questions, right? But if I give you one example that is like a trypsin, for example, the most famous protease we learn in biochemistry class. So this is a serine protease. You have chapters that explaining this, the mechanism how the protease actually cleave the amide backbone of the protein. But if you look at this chapter of the explaining trypsin, which is a serine protease chapter, it actually trypsin recognizes the sequence, recognizes a amino acid, special amino acid, which is the arginine or the lysine. Anyway, they recognize it and then they cleave. So in fact, their directions actually, you have a arginine. So we think about NCC, that amino acid sequence now. Then you have N, arginine means you have a NHCO here, and also you have CONH here. So anyway, the trypsin cleave either this way or that way. So in fact, actually, you do the experiment now, you actually cleave here. Arginine, that side. Okay, so that is, the C side, we call the C side, because the C terminus direction, C side of the arginine, same. So lysine here, then C side of the MI bond is cleaved. So that is the trypsin recognition and then cleave. So this isn't simply one example, but if you think about the papain, other famous protease that cleave the proteins, actually they recognize all the certain amino acid or certain peptide, and then they cleave. So C-side cleavage is very, very normal and the system that I should say. So now if you're considering this, now you can answer this question, the first question is that which histidine tag has to be attached here or this, here or that. So the answer is actually here. So you can think about two cases, some histidine here, and then also histidine here. And then you apply the same principle of trypsin that recognize things and then cleave. So you can recognize things and then cleave. Recognize things and then cleave. Right? So then this is actually cannot cleave. This is a remaining histidine tag on a backbone. So it has to be the N-terminus. The answer is actually N-terminus. Right? The N-terminus is the answer. So it has to be recognizing things and then they cleave. So this is first question, but if you think about it a little bit more, then, so this will be second question. The second question is this. The second question is, then, does a protease recognized histidine 6? This is the answer, the question. So if we luckily have the enzyme that recognizes the histidine sequence and then cleave, then it's very safe to answer that we have any proteins that we want to purify. At N-terminus, you can put the histidine 6, the amino acid, the peptide actually, then use the enzyme that cleave after that. But actually, does the protein recognize histidine, does it exist or not? No. So there's no such a protease exist. So you have to actually use another recognition sequence for this removing histidine tag. So this is actually a big task for protein purification. Actually, that's why it's always used not to use histidine tag. I mean, if you can use this ion exchange or gel formation chromatography or salting out, that we will mention later on this topic. But it's actually better because you have a histidine tag and it seems to be easier to purify protein because you have a histidine tag NTA resin you bring out, pour the solution, and then purify the protein. But it has to be removed. That is the challenge. So then there's no protease that actually recognizes this histidine sequence. But then can we actually histidine 6 and then real protein that we want to purify, the histidine 6, and then cleave, then can we actually put K, which is lysine or the arginine, here and use the trypsin? The answer is no, you cannot use it because, well, actually they will cleave here because they recognize arginine, the lysine cleave, but actually protein has a lot of K, right? Then they actually cleave. So actually this trypsin mess up this protein. So it's a real problem. So that actually the enzyme has to recognize such a very unique peptide sequence. The peptide sequence has to be long enough to not to intercommunicate it to other enzymes. So it has to be unique. It has to be very specific. So I will introduce the very specialized the enzyme, which is called enterokinase. So this is Enterobacter bacteria. The name is Enterobacter. And then people purify this unique the enzyme from this bacteria. But this recognition sequence is very unique. So then D, and you got 5D, which is aspartate, and then 4D, and then we got a K, and then cleave. So this is cleavage. So this is aspartate, ASP, aspartate, the 4 aspartate, and then lysine. How many probability? What is the probability of this? I mean, coming here, 1 out of 20, coming here because we have 20 different amino acids. So times, so this is 5. This is probability to come this sequence. So it is nearly impossible for the regular protein to have this K sequence. So that's why people like to use enterokinase. So then, how you design this then? Now we have a 6, we have a histidine 6, and then 4 aspartate, and then lysine, and then the protein that you want to purify. So that this enterokinase comes in play, they actually cleave in here. So now you end up with this protein that you want to purify. So this is the thing, but I have to put this one. There's also a disadvantage. I'm sorry about just keep saying disadvantage, but you have to think about it. I mean, this, you have, say, his tag, I will just tag D4K and a protein solution. This is a solution dissolved. And then you put the enterokinase. This is enzymatic reaction. This is chemical reactions, right? Biochemical reactions. And then the product is your protein plus enterokinase plus is a peptide remaining before K. So this is 11 amino acid. 6, 4, 1. 11 amino acid. Peptide is such a relatively long molecular weight because average molecular weight of amino acids is 110. So this is about 11 amino acids. So more than 1,000 Dalton molecules. It's a relatively big molecule. So anyway, you have to purify it again. So you have to purify this one. So you need another chromatography. You cannot use other regular, in this case, NTA nickel affinity reagents, because you have to. Is now the histidine tag is gone. So you have to use probably gel formation chromatography, which is size exclusion chromatography, because they are different sizes, probably. So that is another chromatography required. So this is I mean, in the former process to have this target protein purifying using this tag is easier, but the problem is actually when you remove this and then purify again, it actually requires time and more step. So you can balance, has to design, when you design the protein purification experiment, actually, you have to design this whole thing so properly. So I forgot to mention this molecular weight of enterokinase is 47 kilodalton. So then if target protein you purify nearby approaching this 47 kilodalton protein, then even you cannot use a size-based separation technique because if the two things are similar. Then you have to think about ion exchange or other things. So previously we mentioned about the affinity chromatography, NTA nickel system, but we focus on more protein size and which part has to be, the histidine tag has to be existed. So then the next topic, this is actually final topic. So size, charge, and then affinity system, and then this is the last one is salting out system to purify the protein. So we have 4 options actually you can use it. The salting out, and I will explain this one later. The salting out is it's extremely simple. There is no actually the column based the devices is not required. So the previous old things and 3 techniques you have to have the resin, the plastic column, buffer, illusion solutions, and those kind of things. But this one doesn't require such a column resin materials. So that basically now this is basically you utilizes the unique individual solubility of each protein. Because all the protein has a little bit different solubility in the solutions, right? So say if you imagine you have 4 different, say number 1, number 2, number 3, number 4 proteins here. They're basically their size is different, surface charge is different, which is applying for the ion exchange chromatography. And then also other factors that a variety of things that determine different solubilities. You can imagine even small molecular cases such as you have drugs, for example, chemical drugs, antibiotics, and then sugar, based glucose and sucrose and things. The solubilities is a lot different between the molecules, right? So you utilize the system. This solubility of A, number 1, 2, 3, 4, they're all different. As similar to the molecules, their own solubility is different. So how we do it, then now we put the salt. Simply in the solutions, right? The salt, say that the representative salt is sodium chloride, so that 100% ionization, Na plus and Cl minus. So if you dissolve this 1 molar of sodium chloride, then you got 1 molar here, 1 molar here in the solutions. But when you dissolve Na at the same time chloride, then the water molecules has actually come like hydration layer, right? This is OH like this. This is hydration layer form. Hydration, I don't know what this is. The spelling is not correct or not, but anyway, hydration layer is formed. So that is we call this bound water. So these kind of things are called bound water. The bound water means this is actually water molecule H2O, but it's not actually solvent anymore. This is not a solvent anymore. Because the solvent has to be used when you dissolve the solute, S-O-L-U-T-E. Solute comes, and then they hydrate it with water. That is a dissolution. When you add the sugar in water, sugar dissolve it because of this water surrounding in this molecule. So that the surrounded water, which is a bound water, is not a water molecule anymore. That means imagine you have a certain volume of water, you put a lot of salt or a lot of sugar. There's a certain point that even if you add the sugar, but actually sugar does not dissolve and powders come in the bottom. But actually you see still water, still look like water because they're flowing, they just the room temperature, they perfectly look like water except for the sweet taste. But why additional sugar is not dissolved? Because even if they water molecule, but they already used to dissolve the previous sugar comes into the water, they already used all the water molecules to dissolve the previous sugar molecule comes into water. So it look like water, but not a solvent anymore. Solvent has to be dissolved in solute, but it's not a solute anymore. No solution, the solvent anymore. Similarly like this. So you have now, say, H2O layer comes in here because they dissolve the protein. It's like think about analogy of the sugar. But you add the salt. But now the solubility of the salt is higher. This is the solubility of the salt. It's higher. This is a huge molecule, but 3 nanometers is like a really huge nanoparticle, like a molecule is protein. Then you add the salt, and then there's a solubility is higher. Then water actually comes. The remaining solvent water comes to hydrating this ion that we put. But as you add more and more of this, then now, because solubility is higher, this water molecule actually used for dissolving protein, right? This is the previous water that dissolved protein. Now, transfer. So this is important, right? This is transfer to the salt. Salt you added. Because the salt is more it's a charged molecule that has to be water molecules can easier to go. It's a more stabilized energy of the solvent. So you add a lot of salt, then you actually has to remove the layer that dissolves the protein. That actually is number 2. Number 2 has a little bit more hydrophobic property on the surface. That is, the solubility is relatively low. Then this protein is the first protein that actually dissolve and use the powder. So the number 2 is not a solution anymore because that water molecule that forming the hydration layer of the protein number 2 is not occupied anymore. They steal this salt is stealing this H2O to dissolve it by themselves. You add more, then if this is a second lowest solubility in this 1, 2, 3, 4, then they will out into the bottom. So actually you can precipitate it, this protein 3 and 4. So depending on how the salt, it's very easy. I mean, all you had to do is just adding the salt gradually, not all of them. I mean, gradually, because you have to provide enough time to make water molecules to stably dissolve this salt you added. Okay. So this is salting out. So you can precipitating one by one the protein depending on the protein's own solubility. So now the series I mentioned before here at the top. So which salt has to be used? So the question is which salt then? Which salt must be used for salting out? Which salt must be used? That's why I put this Hofmeister series. That this is the ionic strength. That means this higher in this series that occupying more, so occupying more number of H2O to form the hydration layer. From a hydration layer. So occupying more number of the H2 to form the hydration layer. So in this series, even if you have 1 to 1, so you have one of this, then one of this, then you actually maybe probably 10 water molecule has to be used to form the layer. This is where 2 or 3 water molecules can form this layer. So which is more efficient? Then of course this is more efficient. To put this in water, to give a less amount of the salt, then you have a high probability and a faster probability, faster chance to actually pre-dissolve the protein actually precipitate, because you can more number of the water molecules as it becomes. So this is a negative ion. This is a anion, right? This is anion series. So I did the positive ion series that I will mention. This positive ion series that has cation. Cation, we have the strongest one is NH4 plus and K plus, and then A sodium plus lithium, something like this. So this then the question for this, which salt must be used? Then your answer will be has to be this, has to be right. So it has to be this. So what is this one? This is a NH4, right? And then 2, and so forth. Because it's 2 charge, right? 2 charge and 2 plus, since 1 charge. So NH4, 2. This is name ammonium sulfate. The answer is ammonium sulfate is the really good the salt that useful for the salting out process. You probably add 0.5% in weight ratio, 1%, 5% as gradually increase it. All the proteins actually dissolve, salting out from out of the solution. That is one of the good method to purify the protein. So now you learn 4 different techniques, all of it. So now the next class is you actually how to apply the real protein. I will give a case study of how to utilize these 4 techniques in the next class. Okay, thank you for your attention.